Hello and welcome to your linear regression in Python lecture. Just as a reminder, since it's still kind of getting used to things, you can find the blank and the filled out version of these notebooks that I'm going to be coding in on GitHub under in class and lecture notebooks, and you'll be able to find pretty much everything and especially what you need for today. All right, so let us start as usual by running all of our import statements. By the way, you can tell in a Jupyter notebook that something is running by the little asterisks that appears to the left. So the first thing that I want to talk about is basically an implementation of the GOAT part of the lecture that you just watched. And we talked a little bit in that lecture about the fact that we often want to use something like a z-score in order to make our predictor variables on a more similar scale, at least our continuous ones. So I want to show you how to do that using sklearn in Python. So the first thing that we have to do is load in our data so that we have something to z-score. And I'm doing that using the pd.readcsv function and loading in some data that we will look at here. So I'm actually going to replace this line and say homework.head so we can see a little bit what we're looking at. Awesome, so you can see we loaded in this data frame. It has the height, the weight, the diet, and the age of people. And now let's get to z-scoring. So the first thing that we're going to do is build a z-score object. And this object is going to do all of the calculations for us. In sklearn, I'm going to call this z-score. This is called the standard scalar function, and that's what we're going to use to create our z-score object. So this hasn't actually done anything yet. We've just basically created the z-score object. In order to actually z-score things, we need to first tell it what to z-score. So remember that we only z-score continuous variables. And that means that in our data set, we're going to z-score height and age, which are predictors in our model. We're not going to z-score diet because we can't really z-score a categorical variable like what type of diet that you have. So in order to do that, we're going to take that z-score object that we just created and we're going to use the .fit function. And we have to tell it what part of our data frame, HW, do we want to fit our z-score. In essence, which columns do we want to z-score? And we said previously that we wanted to z-score height and we wanted to z-score age. So that's what we're telling it. We're saying from the data frame HW, z-score these columns, height and age. Now, this step of z-scoring basically calculates the mean and the standard deviation needed to z-score our actual objects, but it hasn't performed the z-scoring yet. In order to do that, we need to ask it to actually z-score and then store those z-scores back in our original data frame. To do that, we're going to say, from the original HW data frame, replace only the height and age columns and replace them with z-score.transform and then the data that we want to transform. So again, this calculated the mean and standard deviation needed to do the z-scoring. This z-score.transform actually produced the z-scores, and we're storing them back in our original data frame so that we can use them in our model building. Just as a note here, we can also z-score the outcome, the thing that we're predicting in our model. The reason I'm not doing that here is because we're using something like weight in kilograms that we can kind of wrap our heads around pretty well. So when we look at our actual predictions, it'll be helpful to have it in those units. But just so you know, you can always z-score any of your continuous variables, whether they're predictors or outcomes. All right, let's go ahead and run all of this code that we just wrote. And then let's print out hw.head, which will show us our new data frame that has the z-scored variables for height and age rather than the raw variables that we had earlier. Beautiful. So now you can see height and age are on a very different scale, and hopefully those scales are a little more comparable to help us when we're model building. All right, let's actually build a linear regression model now. I'm going to load in this data, which is some Amazon data on books, and let's look at the head of this data to kind of get an idea for what we're working with. So let's run this. We can see that this data set has the author, the listing price of a book, the price you would pay on Amazon, whether it's hardcover or paperback, number of pages, the width, height, and thickness, and weight of a book. So we are going to take all of this data and we are going to use it to build a model. But before we do that, there's often some cleaning that we need to do with data, or at least we need to check if there's some cleaning we need to do. So the first thing that I'm going to do is something we covered in our Python and Pandas lecture, which is check if there's any missing values in our data set. The way that we're going to do that is with the isNull function. So we're going to say isNull, and then we're going to say sum axis equals 0. And this is basically going to give us a list of all of the columns and tell us how many missing values there are. So let's go ahead and run that. So you can see that there's not a ton of missing values. In fact, the column with the most missing values is weight with only 9 missing values, but we're going to go ahead and remove those so they don't mess with our model building later on. We covered a little bit how to do this. So one way is to say AMA equals AMA.drop NA. And this is going to drop all of the missing values. So any row that has a missing value will be gone from our data frame. Let's go ahead and run that. And now you can see, if we actually run that again, you can see that there are no longer any missing values. Just FYI, it's not really that big of a difference, but one other way we can do that is instead of saying data frame equals the output of drop_NA, we can actually just say ama.drop_NA, and the argument in place equals true. Does the exact same thing. It doesn't matter which one you use, it just want to make sure that you know, so if you see it out in the wild, both of these things do the same thing. So this is a new data set, one we've not worked with before. And when we have a new data set, one of the things we probably want to do is explore that data set a little to kind of get a better idea for the data we're working with. And one really easy way to do that is with the Ggplot function that we used before to make graphs. So for some of the continuous variables in this data set, I'm going to plot some histograms so we can get a sense of the range and the shape of the data for some of our columns. So remember, the first argument to Ggplot is what data frame we want to use, which is our AMA, Amazon data frame. And then we have to tell it what we want to plot. So let's start with list price, which is one of the variables that we have in our data set. And I would like to make a geom histogram. And I'm going to say color equals black and plus theme, there we go, minimal. The last two things that I did just for aesthetic reasons, but of course we always want our graphs to be clearly communicating, so hopefully it helps us do that. So we're going to go ahead and run that and look at the range of the list price. So you can see, probably as expected, most books less than $20. We can see that over here by this really huge peak, but there's some really expensive books. I'm not even sure what this is, but it seems like it's maybe $150, so it must be a very special book. Let's take a second to look at some of the other continuous variables. So for instance, we can look at Amazon price. Let's look at that. Cool, so you can see that it has almost an exactly similar distribution to the last one, which isn't surprising. Maybe they're slightly cheaper, which makes sense because Amazon has always prided itself on having slightly cheaper prices, but overall looks about the same as list price. Finally, just for the sake of time in this lecture, I'm going to look at the thickness of the book, and let's run that. So you can see that this measures the thickness of the book. Again, not anything too surprising. We have some really thick books, we have some really thin books, maybe things like children's books, but everything mostly is in the middle. Now, if this were a new data set to you that you'd never seen before, in real life, you would want to take a little bit more time to explore all of the different variables. However, just for the purposes of this lecture not being a million years long, I'm going to skip the rest of the variables, though please feel free to make those plots on your own. Now that we have sufficiently explored our data and we've cleaned it up a little bit, let's go ahead and build our model. So we are going to use the predictors listing price, num pages, weight, thick, height, and width to give us information about what the Amazon price would be. So we're using all of these variables as predictors, and our outcome, the thing that we're going to predict, is the price that a book would be on Amazon. So now that we have a list of our predictors, let's go ahead and create our X and our Y variables. X contains our predictors, Y contains the thing that we are predicting, and this is something that's going to be consistent throughout all of the predictive models that we use. So we're going to select from our data frame, which again is AMA, which variables we want to use as predictors, and we actually stored that in the list predictors. And then for Y, we're going to say which column contains the value that we're going to predict, which we said is AMA bracket Amazon price. All right, now that we have our data, let's go ahead and z-score. So remember, the first thing to do when z-scoring is create a z-scored object using the standard scalar function. This hasn't done anything yet, it just set up the z-score object. So now what we have to do is tell it what data we would like it to z-score. In this case, it's actually our entire X data frame, because there are no variables that we don't want to z-score. If we had a categorical variable or another variable that for some reason we didn't want to z-score, we'd have to leave it out. But for now, we're going to say .fit and use all of X because we want to z-score all of X. Now, z-score.fit actually calculates the means and standard deviations, but does not actually produce the z-scored variables. To do that, we need to use the .transform function. So I'm going to create a new variable xz, and I am going to say z-score.transform X. So this is saying take those means and standard deviations that you already calculated and apply them to create the z-scores for the data frame X, store it back in the variable xz. All right, let's go ahead and run that. And now that we have our z-scores, we can actually create and train our model. So the first thing that we're going to do is, similar to z-scoring, we're going to create our linear regression object. I'm going to call ours LR_model. And then we're going to use the linear regression function. And this is going to create kind of an empty template for linear regression. We haven't done anything yet, but we have the object to do. Now that we have our blank linear model, let's go ahead and run that. And then let's fit it. So remember, in sklearn, the general way that we do things is to create an empty model, and then the next step is to fit it. And so we're going to say lr model.fit, and inside the parentheses, the two arguments that we need are the x data, so what our predictors are, and the outcome, or the y data. So for us, those variables are stored in x, z, and y. And note that I'm using the z-scored data to train the model, not the raw data. And once we do this, our model is actually going to be created. All right, now that we've built and fitted our model, we can use it to make predictions and also to test how well the model actually did. So let's see what the model thinks are the predicted prices for the various books in our data set that we already have. That way we can compare the predictions to the actual prices that we know and see how accurate our model is. So to do that, we're going to create a variable. I'm going to call mine price pred, and we're going to say our model, lr model, and we are going to use the .predict function. And this .predict function says take the model that you fit and whatever data you put it as the argument, pull out predictions for those data points. So I want to know what its prediction is for all of the books in our data set. So I'm going to give it the XZ data frame again. And when we run this, this is going to show us what the predicted values are, or the predicted Amazon prices are for all of the books in our data set. Since that's a lot of books, I'm actually only going to print out price pred the first 10 so we can see a sample but not have to look at hundreds of them. So let's go ahead and run this. Beautiful. So you can see what our model predicted was the prices for these various books. And now we can use this to see how accurate our model is. In our more theoretical lecture, we talked a little bit about the mean squared error, which is a great way to assess how well our model is doing. And so I'm going to plug that in here, mean squared error. This is just a function in sklearn, and it can calculate the mean squared error of your model for you. In order to do that, we're going to need to give it two arguments, the actual values and the predicted values. Our actual values are stored in the variable y. If you want to see where we did that, would be right up here. And the predicted values, well, that's just price pred, the variable we just created. So when we print this out, this is going to tell us what the mean squared error is for our model. So you can see that we have a mean squared error of about 10.6. Remember that mean squared error is always in terms of whatever the units are of the variable that we're predicting. In this case, it would be dollars. So a mean squared error of 10.6 means that on average, we're about a little more than $3 off in our prediction, which is actually quite a lot compared to how much books cost. By the way, if you ever don't want the squared error, but the absolute error, which is sometimes a little easier to understand, you can always use the mean absolute error function as well. Now, as we talked about in our theoretical lecture, mean squared error is a little hard to interpret sometimes because it always must be contextualized within whatever the units of your outcome is. So we can also calculate for linear regression an R-squared score, which will allow us to have a unitless way of assessing how well our model did. Again, this R2 score function takes the actual values, comma, the predicted values. So we're going to give it y and price pred. And when we run this, this will tell us the percentage of variation accounted for by our model. So in our case, it's about 92%, so that is not shabby at all. There's still a little room for improvement, but overall, we're predicting a lot of the variability in price. Just as a note, it didn't happen here, but as I mentioned in the lecture, it is technically possible because of the way sklearn calculates things to get a negative R-squared score, and we'll talk more about this when it happens, but just so you're not surprised the first time that happens to you, remember the R-squared score can also be interpreted as whether our model is doing better than just predicting the mean for everything, and the higher the score is, the closer to 1, the better it is at predicting. A score close to 0 means we're basically doing no better than just predicting the mean each time. All right, it is everyone's absolute favorite time, which is to do assumption checks. Now, I mentioned in our lecture that there are quite a few assumptions that linear regression makes, and one of them that you may have heard of in other stats classes and people may focus on is the assumption of normality. Now, we're not going to focus on that assumption as much in this class, and the reasons for that are a little bit more complicated than I want to get into, but just so you know, to give you the TLDR, it's actually very difficult to assess normality in a way that is meaningful and helpful to your models. So there are ways, and one of my favorite ways to assess normality is with something called a Ggplot. I've linked something here in case you're interested in how to do that in Python, but we're going to move on to some of the other assumptions. In order to assess the two assumptions that we're going to focus on mainly in this class, homoscedasticity and linearity, we are going to need to make a residual plot. So to do that, we have to grab two things, our residuals and our predicted values. And remember, residuals are just the difference between what we predicted and the actual value. All right, so we are going to create a data frame called a sump which is going to store the variables we need to make our residual plot. So we're going to say pd.dataFrame, and we're going to have two columns in this data frame. The first is error, which is going to be our residuals, the difference between our actual values and our predicted values. So we're going to say y minus price pred, and that's going to be our actual minus our predicted. And the second column, I'm just going to call pred, and we're just going to store the actually predicted values. So once we run that, we're going to have our data frame that we need. So let's use it to make a residual plot. To do that, we're going to pull out our trusty ggplot functions, and we're going to say from the data frame asump, comma, AES, x is going to be our predicted values, so that's going to be on our x-axis, and our y-axis is going to be our error. Using those, we are going to make a scatter plot, so I'm going to add geom point, and then just for aesthetic purposes, plus theme minimal. All right, so before I run this, I just want you to take a second and think, if our model had very little error, what would we expect this plot to look like? Beautiful. So we can see that our plot tells us a lot about how the model is actually doing. Our predicted values are on the x and our error is on the right. And remember that in general, the lower the error is better. So the closer to 0 that our errors are, the better the model was at predicting that specific data point. Let's focus on the assumption of homoscedasticity first. So we talked a little bit in the theoretical lecture that homoscedasticity is the idea that the errors are pretty evenly spread across the different values that our model can predict, and that there's not a certain range of values for which our model is way worse or way better at predicting. And what we're looking for in this plot is that even spread. So you can see as we look from left to right across this graph, we're looking for any indication that there is an uneven spread in how the data points are spread out. So you can see here that this actually is a bit hard to assess, and that's pretty much always the case in these real life data sets. The spread is actually pretty even here. It's pretty clustered around 0. It's a little bit spread out, but as we get to larger predicted values for books, our model tends to be a lot more wrong. However, the problem here is that we only have a couple of data points, so it's hard to tell if this is a consistently heteroscedastic pattern, but it's definitely something that we want to note and be a little concerned about. In this specific context, heteroscedasticity, meaning that there's less error over here for lower priced books and a lot more error for higher priced books, basically means that if we're using our model in real life to predict these books, we really can't rely on the predictions that we make for more expensive books because they're wrong quite often. However, because of that heteroscedasticity, we actually can rely a lot more on the predictions for lower priced books because they tend to be a lot closer to 0 error compared to the higher priced ones. Now, heteroscedasticity is problematic. However, oftentimes what we have to do when we see heteroscedasticity, or at least we're worried about it, is to see if we think that it'll cause problems in our specific context. Maybe for us, we say, well, high-priced books are so high-priced, people won't really mind if our predictions are $10 off or $20 off because they're already paying hundreds of dollars for that book anyway. Or we might decide in other contexts that the heteroscedasticity is very problematic and that we maybe don't want to use something like linear regression, which relies on the assumption that there is homoscedasticity. All right, we'll look at more examples of heteroscedasticity and homoscedasticity later on, but for now I want to focus on the assumption of linearity. Now, linearity is actually pretty easy to assess in a simpler way, variable by variable. So for instance, I'm just going to pause here and say we could make a Ggplot with the AMA data frame, and we could say AES, X is one of our predictors, so we'll say list price, and Y is the thing that we're predicting, which is Amazon price. And we can make a geom point, and then of course plus theme minimal. And we can assess linearity for 2 individual variables this way. So in this type of plot where we're just looking at a single predictor variable on the x and the outcome on the y, the way that we look for linearity is by looking to see if there's any clear patterns that indicate that there's a nonlinear relationship. We talked about in the other lecture that might look like an exponential curve, it might look like a U or a W or a sine wave. There's infinite ways for something to be nonlinear, but what we're looking for is something that is roughly a straight line, even if the data points are very spread apart. So in this case, we can see that the assumption of linearity pretty much holds for these 2 variables. The relationship between list price and Amazon price is not perfect, but it's definitely well described by a straight line. Now, we can repeat this for all of our predictor variables, and technically we should, but I want to tell you, just scrolling up a little bit, that we can also assess linearity from this residual or error plot that we made for hetero and homoscedasticity. The way that we look for nonlinearity here is kind of similar to in the other graph, but we're assessing all of the variables together instead of one at a time. So when we look at this graph with linearity in mind, we're looking for nonlinear patterns. So is the pattern of dots described by something that is not just an amorphous blob of points? If there is a very clear pattern, then we're suspicious that there's some nonlinearity there, and we should actually go in and check each individual continuous predictor, but this is just a good way to get an overall sense for whether the assumption of linearity holds. Now, I just threw a ton of information at you, so let's look at a couple examples where these assumptions are or are not violated and see what the residual plot looks like so you can better assess them. All right, so I've made up a bunch of data, and I want you to think about, as I plot this data, this raw data, what you think the residual plot would look for when we fit a linear regression. So let's go ahead and run this, and you can see it. This is the raw data. On the x-axis is our predictor, on the y-axis is the thing we're predicting, and you can see here, hopefully, that there is a very clear non-linear relationship. Now, if we're fitting a linear regression, the only thing we can fit is a straight line, which isn't going to fit very well. So let's see from this raw data that we're seeing, what would the residual plot look like in terms of being able to tell us whether there's homoscedasticity and whether there is linearity. So I'm going to go ahead and do what we did before, which was to fit a linear model and then create that assumption graph that we made before. Beautiful. So we can see that this graph looks very different from the one we just looked at and is very clearly non-linear. So this is an example of what I was saying before. You're looking for clear patterns of non-linearity because you can see here, this is not an amorphous cloud of points. It is a very clear non-linear pattern. So this tells us that there is something going on in our model that is not linear. And if there were multiple predictors, we would want to individually plot them. However, there's only one here. So we can tell specifically that the relationship between x and y is non-linear. However, in terms of homoscedasticity for this graph, it's actually not quite as clear. The homoscedasticity says that there's equal variance kind of as we go from left to right. It's not that there's huge amounts of variance one place and tiny variance in another. And so we can actually see here, there might be a little difference, right? There's maybe slightly less error at the ends of our graphs compared to the middle, but it's not enough to make me super concerned about heteroscedasticity. Let's look at this next set of data. And again, we just have one predictor and one outcome. And again, we can see that there is a very nonlinear relationship in this raw data. But again, a linear regression can only fit a straight line as a model. So think about, as I scroll down to run this code, what do you think that this residual plot is going to look like? And how would you assess it for both homoscedasticity and linearity? Beautiful. Okay, so we can see our residual plot on the screen, and as with the pattern before, it is a different pattern, but there is a clear pattern of nonlinearity. That makes us suspicious, and again, if there are multiple variables, multiple predictors, we want to look at them each individually. Here there's only one, so we know that the nonlinearity is between x and y, and also we would want to assess for homoscedasticity. It's a little bit hard when there's a big pattern like this, but what we're looking for here is, are the errors roughly equally spread out, or are there some areas where there's huge errors, some where there's not? I would say there's nothing to make me too concerned. We're probably way more concerned here about the nonlinearity, but again, at the very edges of the model, maybe there's a little bit less spread of error compared to the middle, but again, nonlinearity is kind of the big red flag here. All right, let's look at this next data set, which has some spread. It's nothing that is clearly nonlinear, but we're not super happy with how spread out the data is. Now, think about this model again. I don't see anything inherently nonlinear here, but let's check out our residual plot as well so we can look at both that and the homoscedasticity assumption. So as you can see here, this looks a lot more like that amorphous cloud that I was talking about, because this, in this case, is a relatively linear relationship. Remember that a linear relationship doesn't have to be a perfect straight line. It just means that there's no clear nonlinear relationship, kind of like the last two examples that we looked at. So this one, at least, partially ticks the box for linearity. I'm not really concerned about nonlinearity here. However, I am getting a little bit concerned about heteroscedasticity. So remember, homoscedasticity, our assumption, is that there is about equal amounts of variance across the entire model, and that is clearly not the case here. And the way I can tell is that you can see over here at small predicted values, the error is almost non-existent. There's very, very little error here. And as we get bigger and bigger values, you can almost see this kind of fanned out shape, or this like cone shape, where the error gets bigger as the predicted values get bigger. This is not the only pattern of heteroscedasticity that's out there, but it is one that shows up a lot, where there's one edge of our model that has very little error, and then kind of this cone shape where the error balloons out at the other end. And this is really problematic, one, just because it's breaking an assumption of our model, and assumptions are things we assume to be true, and if they're not true, that's not great, but also because of what this means for the predictions that our model makes. When we have heteroscedasticity like this, you can see that we have a little bit less trust in areas of our model that are higher and a lot more accuracy in areas of our model that are lower. And this basically can be problematic in real world settings because it means that there's a group of a certain predictor or a range of a certain predictor for which our predictions may not be accurate. For instance, if we were predicting the amount of money that someone would get from welfare or the amount of points someone would get on an exam or something where it matters whether that prediction is high or low, heteroscedasticity means that for a range of values, we're a lot more wrong. For instance, if we were looking at predicting test scores for students, like they actually did during the COVID pandemic in places like England where they have those kind of end of year tests, we could be causing a lot of issues. For instance, if we had a pattern of heteroscedasticity like this, that would mean that for low scores, people who did really poorly on the test, our model pretty accurately predicts that. But when our model predicts someone does well, we could be incredibly wrong because of how spread out the error is. And again, sometimes we might not care about this, especially if we just care how accurate the model output is. We don't really care about when it's accurate. But it's really important to think about these assumptions and what effect they might have in the context of whatever data set you're using. All right, now that we've looked at a million plots to check our assumptions, let's look at our coefficients. So remember that our coefficients are able to tell us how the relationship between the predictors and the outcomes vary. And so what we're going to do is we're going to grab the coefficients from our model and just take a look at a table of them. So what I'm doing here is I'm creating a data frame and I'm grabbing the coefficients from our model using our model.coef underscore, that underscore is important, and that just grabs the coefficients from a model if the model has already been fitted. And then just for our ease of like seeing it, I'm adding a column with the name of each predictor so that we'll be able to have one column with the name, one column with the coefficient. Now, because our model coefficients for some reason in sklearn don't include the intercept of our model, I'm just going to grab that separately using lrmodel.intercept and adding it to my data frame. Okay, so we're going to run this. And once it's run, we are going to print out the data frame, coefficients, if I can spell it, so that we can actually look at and assess our coefficients. All right, so we can see from these coefficients basically what we saw in our previous lecture. We can see that as list price increases, the predicted Amazon price also increases, which makes sense. We can see that as the number of pages increase, so do the predicted Amazon price. Weight is negatively associated, thickness is negatively associated, height is negatively associated, and width is negatively associated, which basically means because these have negative coefficients, as these variables, weight, thickness, height, and width go up, our predicted Amazon price actually goes down. The opposite is true for list price and num pages, both of which have positive relationships, which basically means as list price and number of pages goes up, so does the price. To be more specific, we talked in the previous lecture about how to specifically interpret these coefficients. For instance, as list price increases by 1 standard deviation, remember because we z-scored, we expect that the Amazon price will go up by $11.4. Similarly, let's go to weight. As weight increases by 1 standard deviation, we expect the Amazon price to decrease by 0.41, so about 42 cents. I won't go over all of the coefficients because, again, the interpretations are very similar. However, the one that's different is the intercept. And this tells us, remember, that when all of the predictor variables are 0, this is what we would expect the predicted Amazon price to be. And remember, these coefficients are basically the way that the linear regression model predicts the price of a book. It takes the actual predictor values, multiplies them by the coefficients to get the actual predicted price. And I just want to quickly show you that by hand so that you know what linear regression is doing when we call that .predict function. So here you can see I have a line of code that is basically saying predict the price for this new book. This book that has a $12.45 list price, is 300 pages, 10 ounces in weight, 0.8 thickness, 8 height, 5 width. So what we're going to do is we are going to z-score all of these variables because remember our model is built on z-scored data, so we need to z-score anything that goes into it. And we're going to do that by creating a new variable, and we're going to call that new book z. And we're actually going to use the z-score object we already fitted, and we're going to go ahead and use that to z-score our book data. The way that we do that is by saying z-score.transform new book, book, there we go. And this is going to create a z-score version of our raw data for us. Now that we've done that, let's go ahead and see what the .predict function gives us. So we have our model, LR model. We can say .predict new book Z. And this is going to tell us what our model thinks is the predicted price of this book. You can see here that our model thinks that the book will be about $8.42, and we are now going to recreate that number by hand just to prove to ourselves how linear regression works. So really quickly, what I'm doing in this cell is just adding a 1 to our predictors that represents the intercept. You can see they're exactly the same, just now there's a 1 at the end for the intercept. And now let's go ahead and do that multiplication ourselves. So we can use the np.sum function. And what we're going to do is we're going to say, take our new book inter variable, so remember this is all of our predictors, and just multiply it by the coefficients from our data frame. So we're going to say from coefficients bracket coef, so that's going to grab all our coefficients and multiply each coefficient by its respective predictor variable, and then we're going to take the sum of them so that we can prove that this way of doing the math by hand is exactly the same as what the .predict function is doing. So let's go ahead and run this, and you can see that except for a little bit of rounding, our answer is exactly the same as that we got from the .predict function. Again, I'm not going to make you do this by hand a lot. I'm just wanting to show you that this is exactly how linear regression gets its predictions when you use the .predict function. All right, last but not least, let's go through very quickly a linear regression model from loading in the data all the way to assessing our model. So we're going to use this Spotify data from Beyonce that we're going to load in, and we can see that we have a ton of variables that tell us something about the different songs that Beyonce has put out. And our goal with this model is to predict danceability, which is a continuous value where high values mean like a very danceable song and low values mean not so much. So in this model, we are going to use the variables energy, key, loudness, speechiness, acousticness, instrumentalness, liveness, and valence, which are all various continuous values in our model, in order to predict that danceability. So now that we have those predictors, let's go ahead and create our X and our Y variables. So we're going to go ahead and grab our predictors and store that in X. That's going to be B, our Beyonce data frame, bracket predictors, and then Y, which is going to be B, bracket the name of the column we're going to predict, which is danceability. So let's go ahead and run that. All right, now that we have our X and Y data, we're going to go ahead and Z-score. So the first thing that we do as normal is to create a Z-score object, standard scalar, there we go. But this time we are going to just Z-score our continuous predictors. And if you scroll up to our data frame, you can see that key is actually referring to what key the song is in, which is not necessarily a continuous variable in the same way that things like energy, loudness, acousticness, instrumentalness, all of our other predictors are. So we are actually going to Z-score only the variables that are continuous, which is basically all of them except for key. To make my life a little easier when doing this, I'm going to make a new variable called cont predictors, there we go, which is going to be a list of all of the variables that are continuous, which is all of them again, but key. So now our process is going to look very similar to what it has before, but we're just going to do it on the continuous variables. So we're going to say zscore.fit, and we're going to say X bracket cont predictors. And then once we fit our data, we actually need to calculate the z-scores. So we're going to do that by saying X bracket cont predictors equals z-score dot transform X cont predictors. And so you can see here that this process is very similar to what we did before. We're just leaving out our non-continuous variables, but we're still doing the create an empty model, dot fit, and then dot transform. Once we've run this, I'm going to go ahead and print out X just so you can see the z-scores in practice and that we didn't z-score key. Let's go ahead and run that. Beautiful. So you can see key remained unchanged, but all of our other predictors are now z-scored. All right, now that we've done that, we can actually create our model. So I'm going to call it Bay mod, and I'm going to say linear regression because, oops, I spell that right, because I'm creating an empty model. And then I'm going to fit that model. So I'm going to say Bay mod.fit. We give it the X variables, the predictors, and then the Y. So that's going to be X, comma Y. And now that we have a model that's fit, we can go ahead and run that. And now we can assess how our model did. So I'm going to create a new variable called dancepred and set it equal to Bay mod.predict X. So this is going to give us the actual predicted values for our model, and we can use that again to assess how good our model is. One way to do that is using the mean squared error, there we go, which we give it the actual values, which is in Y, and then the predicted values, which we just created in dancepred. And this, when we run it, will tell us what the mean squared error is. And again, hopefully you can see in the comparison between the Amazon prices and this model that's predicting danceability that there's no one rule of thumb for how good of a mean squared error you can have, because these two things are very different scales, prices versus danceability. And so this tells us that the mean squared difference between our prediction and the actual value is about 0.12, which is relatively low, and we just have to contextualize that within what the scale of danceability is. We could, for instance, do that by making a Ggplot. We could say Ggplot, Ggplot. And we could say BAS X equals danceability plus geom histogram. And then again, I'm going to add my beautiful aesthetic choices, black, plus theme, minimal. Beautiful. So we could, for instance, run this and see that, okay, on average, our squared difference is 0.01. Well, the range of danceability is 0 to 1, so that doesn't seem that bad, but we have another tool to assess the performance of linear regression, and that is our R-squared score, which doesn't depend on the units of our outcome, and is therefore maybe a little easier to interpret in terms of how well the model is doing just generally. Again, we can grab that using R2 score, there we go, and then give it the actual values, comma, the dance pred, the predicted values, and we can go ahead and run that. Okay, so our R-squared is 0.599, so about 60%. So this actually isn't as good as our Amazon model that we did before, but it's still pretty good. Our model accounts for about 60% of the variance, so it's surely doing better than just predicting the mean each time, which would be a value close to 0, but it's not perfect because we would expect perfect models to be very close to 1. Okay, so our model isn't doing perfectly, but it's not doing horribly, and we maybe could add some things to the model to make it do better, but we're not going to do that now. What we are going to do is look at the coefficients of our model. I am doing that by, as usual, pulling the .coef and the .intercept, throwing them into a data frame so I can print them out. Beautiful. So you can see the coefficients, and we can assess something about the relationship between our coefficients and our outcome just by the positive or negative value of the coefficient. For instance, energy, key, speechiness, acousticness, instrumentalness, and liveness all have negative coefficients, which means as those values go up, danceability actually goes down. And on the other hand, loudness and valence, as those go up, because they have positive coefficients, we actually also expect danceability to go up, which makes a lot of sense if you listen to music, that the valence, like the happiness of the song and the loudness of a song, probably makes it a song that you want to like get out and dance to a lot more. Now, I'm not going to go through the interpretation of every single coefficient, though I encourage you to do so just for practice, but I'll go over a couple. Let's start with energy. Remember that we z-scored, so the interpretation is in terms of standard deviations. So the way we would interpret the energy coefficient is as energy increases 1 standard deviation, our predicted danceability score goes down by about 0.03. On the other hand, if we look at a positive coefficient like the one for valence, we would say as valence increases by 1 standard deviation, the predicted danceability also increases by about 0.09. Beautiful. Okay, I think we've done enough linear regression today. I will talk to you next time.